Thank you for coming, everyone. So continuing our Lucy 50th monthly lecture series, we have three talks today, and the theme for today's talk is human adaptability to a changing planet. Very interesting subject. So our first speaker is going to be Chris Campisano. Chris is an associate professor in the School of Human Evolution and Social Change and research scientist in the Institute of Human Origins at Arizona State University. He is also Associate Director of IHO. Chris's broad research interests revolve around the chronology and environmental context of hominin evolution. Specifically, he is interested in characterizing ancient landscapes and their change across space and through time at varying degrees of resolution by integrating paleontological assemblages and depositional environments. He has a strong commitment to active research and has participated in more than a dozen field projects at fossil localities in Ethiopia, Kenya, South Africa, the United States, and India. Currently, he is the PI of the HARA project, one of the three field projects that IHO runs in Ethiopia. So Chris' talk today is titled Climate Change and Human Evolution. Global and regional climate change is one of the primary culprits used to explain the changes we see in the early hominid fossil and archaeological record. But what exactly controls large-scale climate patterns, and how are they manifested in particular regions of Eastern Africa where our ancestors lived? Primarily using data from drill core records near hominid sites, Chris will discuss how we extract climatic and environmental signals from the sedimentary record, what changes we see and what we don't, and how they may relate to critical intervals in human evolutionary history. So please welcome Chris with a round of applause.
All right. Thank you, Johannes. Is this thing working? Yes, no? All right. For everyone still sweltering in the September heat, this is a talk on past climate change and human evolution, not moving forward. So thanks everyone for being here. This evening I'm going to attempt to tackle a very large topic in a very short period of time, so buckle up a little bit. I'm also going to try and keep the climate wiggles to a minimum, but ultimately some of them will show up. So the primary record of human evolution is, of course, the bones and stones. These are what grab most people's attention and, of course, headlines. For me, however, I'm interested in key questions about how we got from point A to point Z and all the transitions and diversions in between. Specifically, I'm interested in the environmental context of the changes we see both in the anatomical and behavioral records. So my interest in the topic of climate change and human evolution actually started when I was undergrad, way back in the 20th century. And the idea that climate change influenced human evolution isn't anything new. It's been around basically since the time of Darwin. However, starting in the 80s, the ocean drilling program had a lot of sort of technological advances that allowed higher resolution and better preserved cores to be collected and dated. And one of the focuses on this was the sort of the initiation and the onset of northern hemispheric glaciation, so things in the Arctic Circle and Greenland and such. And this was sort of around the 2.5 to 3 million year old time interval. So these new data sets spurred a lot of studies at this time interval, and in particular in paleoanthropology, where of course that interval around 2.5 to 3 million years ago was roughly where you start seeing the origins of our genus Homo and the earliest stone tools at the time. And so there was a flurry of studies by that. And sort of the general idea was that northern hemispheric glaciation leads to more open arid habitats in Africa. This leads to a spread in grassland savannas. And this is the driving selective force for the origins of our genus and behavioral changes such as stone tools. In fact, this book here on the left is one I brought with me on my first paleoanthropological trip to Kenya when I was an undergrad. And we'll circle back to some of these studies actually as well. So in terms of events in hominin evolution attributed to environmental change, it would be, I guess, like Johannes said, sort of climate is sort of the main culprit. Anytime there's sort of some event, someone can find some sort of climatic or environmental shift to tie it to. It would be a lot more challenging to come up with a list that doesn't have environmental or climate change as the culprit. But it's important to keep in mind that this picture is painted with very broad strokes, both in terms of temporal correlation and, of course, causality. So again, it's important to remember temporal correlation of events does not equal causality. So all these comparisons here are highly correlated and statistically significant, but clearly they are not causally related, or at least I hope they're not. The one on the bottom right is for our colleague Ian Gilby, who has 2 teenage sons driving and probably very interested in the Ohio presidential results this November. So here's your first climate wiggle. As I was talking about, the ocean core data that was collected primarily in the 80s and 90s is constructed, the climate record are constructed from the shells of these little unicellular critters here called foraminifera. They live sort of at and in the bottom of the ocean floor. And the isotopic signal recorded in their shells is a way to record essentially glacial volume, right? Different type of water chemistry. And when these are studied, you can see that the onset of northern hemispheric glaciation here at around 2.5 to 3 million years ago, and then sort of people focus really on that in terms of, well, how does this tie into the human evolutionary record, but other periods too in terms of the intensity of cycles changing at around 1.7 million years ago, and then even more intense and longer duration glacial cycles at around 1 million years. So this, for the last 3 decades, has sort of been the background for a lot of studies in climate change and human evolution. And we're going to focus on sort of a little bit of what controls the patterns we see here. So we're going to zoom way out here because a large part of global climate patterns can be explained by the physics of the variations of the Earth's orbit around the sun. In particular with solar radiation in terms of how much solar energy is focused on a particular spot on the ground and how that changes over time. And there's 3 sort of main controls we talk about. So the first is eccentricity. Our orbit around the sun is not a perfect circle, and in fact it varies from being pretty much a perfect circle to more elliptical. And this goes back and forth about every 100,000 years or so. Right now we're actually closer to being a circle, and the difference between when we're sort of nearest to the sun versus farthest from the sun is about a difference in average global difference of about 7%. When this is at the extremes, it's about 17%, so it's pretty substantial. If you guys remember your globes back in elementary school or so, we actually still have one at our house. It's not vertical, right? It's tilted at 23.5 degrees, just like Earth is in terms of the orbit around the sun, or the plane of Earth's orbit. This also changes between 22.5 and 24.5 degrees. And that controls seasonality, or amplifies seasonality, I should say, because if the Earth was vertical, right, on a 90-degree axis, the sun would basically sit at the equator as we go around the sun's energy at the equator, and we wouldn't have seasons, right? And so we're sort of midway in seasonality. If you're tilted 24.5 degrees, you have more seasonality, right? Your differences between summer and winter. And if you're closer to 22.5, it's diminished a bit. So remember, when it comes time for the holidays, that in fact, axial tilt is the reason for the seasons. The third sort of control is precession. And this is sort of like a spinning top, if you will. So it interacts with eccentricity, that sort of roundness of our orbit, on these 20,000-year cycles. And this has to do with the timing of where we're at in that orbit in different seasons. So right now in the northern hemisphere, our summers, when we're tilted towards the sun, we're actually furthest from the sun. And when we're tilted away from it, our winters, we're closest to the sun. So our seasonal, in the northern hemisphere, the seasonal differences between summer and winter are not as strong as they could be. This is the reverse for the southern hemisphere, right? In the summer, when they're tilted towards the sun, they're closest to it. We'll have that situation in about 11,000 years, and we had it about 11,000 years ago. 11,000 years ago is also when we basically exited the Ice Age, right? So this has controls on the energy of solar radiation on the surface of the Earth. So here are sort of these different cycles in a visible sense here. So you see precession, obliquity, and eccentricity, and they kind of interact with each other because 20, 40, and 100,000 years ultimately go together. And these are called Milankovitch cycles. They're named after Milutin Milankovic, who is a Serbian astronomer, geophysicist, climatologist, structural engineer, sort of all-around smart guy. And he did most of this work around World War I. But these are predictable, mathematically calculatable parameters for how much solar energy or radiation will hit a spot on the Earth and how that changes over time. And we'll talk again about how these 20, 40, 100,000 year cycles can be manifested in the sedimentary records we see. So you can think of Milankovitch cycle as kind of like a metronome, right? They're sort of keeping the pace of global climate. It would be like the bass player in a band, right? So the tune changes a bit, but it's pretty much keeping beat and sort of constantly throughout Earth's history. But it's not the only player in the band. So there's lots of other variables, one of which would be something like plate tectonics. So over time, they're controlling the position of continents, right? So 5 million years ago, you used to basically have an equatorial current around the Earth, right? North and South America were disconnected. You had a pretty big gap north of Australia. When those things closed, somewhere around 3 to 4 million years ago, you start redirecting water. And when you redirect ocean currents, you redirect heat around the planet as well. And this has created sort of our modern ocean circulation. You also end up with things like El Nino and a version in the Indian Ocean called the Indian Ocean Dipole, which controls weather patterns, particularly precipitation. There's also mountain building for rain shadows. You have the uplift of the flanks of the Rift Valley while the bottom drops out, so very altitudinal gradients as well in different environmental conditions. So while Milankovitch cycles are sort of this bass player, you have all these other lead guitars doing sort of their thing and playing whatever they may play on top of that background rhythm. So going back to this framework real quick, you can see how these cycles are actually manifested in these global climate curves from ocean cores. So the 20,000 year beat of precession is sort of what happens before northern hemisphere glaciation. And that slide towards glacial conditions is actually a transition from 20,000 years to 40,000 year cycles. The 20,000 year cycles are there, they're just sort of being overshadowed by the 40,000 year obliquity cycles. And if you look, starting around 2.5 million years ago, you can see those glacial cycles, right? They're not super big, but then around 1.8 million years, actually the intensity of sort of the dominance of that 40,000 year cycle becomes more intense, and you see larger glacial cycles happening. And around 1 million years, we have a transition to a dominance of 100,000 year cycles. And that's when you get these very strong, long duration, high amplitude glaciers. And so, again, this is sort of this backdrop, and we know that these are being controlled, amongst other things, but a lot of it by these Milankovitch cycles. When it comes to environmental hypotheses in human evolution, there's sort of 3 different flavors or conditions you can imagine. You can have stable habitats, right, where not a whole lot is going on. You can have progressive habitat change, where you go from very wet conditions to very dry conditions. Or you can have variable habitats where they fluctuate seemingly at random. And it's characterized by variability. This doesn't include biotic interactions or competition or things like that. This is purely environmental. And this is sort of how a lot of hypotheses of human evolution have been couched, right? So in terms of progressive change, we have some examples on the left. Elizabeth Verba from Yale has what's called the turnable pulse hypothesis, and her idea was looking at the records of African fossil bovids or antelopes, that there were sort of these patterns of the origination and extinction of different taxa at certain times, right? They were concentrated around, say, 2.7, 1.8, and here 800,000 years ago. And again, these can be tied to those transitions in global climate. Similarly, you have Peter Domenical looking at ocean core records and looking at sort of these stepwise changes in aridity over time, again, at around this 2.8, 1.8, 1 million years ago. And these time intervals are also correlated, or can be correlated, again, very broad strokes, to events in human evolution, right? So the origin of our genus, origin of stone tools, Homo erectus out of Africa, sort of a lot of the things on that list I had earlier. A little bit later, Rick Potts and several others since have focused less on this progressive climate change or environmental change to more about the issue of variability. So on the right is what's called eccentricity modulated precession. It's one of those Milankovitch cycles. And you can see that there's some wider spots and narrow spots. When you're in the wide spots, right, the wide wiggles, that's a highly variable climate. You have drastic changes in seasonality over time. And what they looked at is like if we identify these high variability intervals, what's going on in the fossil record there? So their view is that, in fact, it is the we're working on complex adaptations that are responsive to these novel conditions, essentially the evolution of adaptability. And that's the lack of environmental consistency that leads to adaptations that are not habitat specific, as opposed to progressive change. So this is a quote from a colleague of several of ours, John Kingston, that sort of encompasses what I was sort of thinking about a while back perfectly, right? Well, it's reasonable to assume that these large-scale changes may have altered climatic patterns relevant to hominid evolution in tropical Africa. Specific local environmental manifestations of these shifts at sites remain generally unknown. Basically, we know that there's sort of this beat in climate, and it probably is affecting equatorial Africa, but the devil's in the details, right? If you're painting with broad strokes, again, you can sort of make everything look like a correlation. And this led, along with others, for us to develop a project I'll be talking about for the rest of the talk, the Hominin Sites and Paleolakes Drilling Project, of which John Kingston is a part of. And our goal was essentially to build on the terrestrial records we already had by collecting continuous paleolake records from basins, critical intervals at the hominid sites or archaeological sites themselves, and then assemble these essentially over the last 3.5 million years. So this is a project that was about 100 scientists or so from 8 different countries. I typically make the joke that before this project, I had a full head of hair and it was brown. We took advantage of lake coring technology because we could use the same equipment, basically. We used the same analytical toolkit. The difference is that when you drill a lake core, like a modern lake core, the first sediment you drill was the stuff deposited yesterday, right? Here, we could drive out to an outcrop and target a lake that started 1 million years ago, or 2 million years ago, or 3 million years ago. And so we learned a lot from outcrops, but drill cores have an advantage of their quality, right? They've been buried for millions of years. They're not exposed to the elements, so they preserve a lot more information that hasn't degraded or weathered. They're typically more continuous because you're essentially in a basin sump, and it's recording over time, whereas outcrops have a lot of erosion. And the resolution tends to be, like I said, higher resolution. So the red are the sites we drilled from northern Ethiopia to southern Kenya. And on the right, you can see sort of the time frames covered and the events in human evolution that are in those time frames. On this chart, you can also see, this map, sorry, the yellow dots are ocean cores. The purple dots are modern lakes that have been drilled, but they only go back 100,000 years or so for most of them. Ocean records go back millions of years, but you're homogenizing a huge area of information. So our goal was to find this middle ground that we can correlate to these other records and look at what's going on basin by basin, because that's sort of, basin populations is sort of where evolution happens. And I have Olduvai on here too, because we sort of had a proof of concept that they took and have also done several drilling projects in Olduvai as well. I'm going to focus just here on the bottom 2 sites, so Baringo and Lake Magadi and Lurgasile. Here's just some pictures of the cores. I'm not going to get into too much details. They're only about 2.5 inches in diameter, so kind of like the size of a Coke can. But these are not the sort of things you see in outcrop at paleoanthropological sites, right? These finely laminated, well-preserved sediments, these rapid transitions from soil to lake that you see here. This is sort of a proof of concept of how well-preserved this material is. Overall, we collected almost 2 kilometers of core for these sites. So the first site I'm going to talk about is the Tugan Hills, or the Baringo Basin in Kenya. This covers about 2.6 to 3.3 million years ago. Again, that's that critical interval coming from no hemispheric glaciation into the onset of glaciation, also covering things like the origins of our genus Homo, stone tools, the Oldowan stone tools, origins of the genus Paranthropus, right, the robust Australopithecines, not all at this site, but during this time. And one of the things we knew from this site, in the right-hand picture, those white beds are actually white lake beds called diatomites. And they're made of these little critters, these unicellular organisms called, actually they're algae called diatoms. And they have basically a shell or a test of silica. And so you can identify these, and what these show is repetitive cycles of deep lakes every 20,000 years. So we thought, well, there's already a good climatic signal here, so let's see what else there is. What was interesting is, of course, we targeted this primarily because of the onset of northern hemispheric glaciation. So we expected all these changes to happen around 2.7, 2.8 million years ago, or any changes we saw on the record. What was interesting is we actually saw most of the changes happen around 3.05, 3.1 million years ago, which is at the end of something called the mid-Pliocene warm period. And this is a well-studied event because carbon dioxide concentrations and temperatures are basically a model of where Earth is currently headed. And so here you can see through these diatoms, these little lake bugs here, that before 3.05, you have basically these river systems, maybe some small lakes, things like that. And then afterwards, you have these rapid fluctuations between very deep lakes, and either very shallow lakes or no lakes at all, again at this 20,000-year cycles. When you look at the vegetation response, this is the isotopic signal of vegetation, right? So C3 is trees and shrubs, C4 are grasses, so basically closed versus open habitats. Before 3.05, it's a dominant C3, tree and shrub signal. Afterwards, it happens to be dominated by C4, right? So grasses. What's also interesting is there's lots of variation within that. So where you're in the 41% C3, you have grasslands that are going from basically 20% grass to 100% grass over relatively short periods of time. And then more on the vegetation is these things phytoliths, so they're basically in the rigidity of the cell walls in plants. And these are also preserved very well in this core. And you can see before 3.05, we have dominantly these wooded grasslands to forest, again, fluctuating at roughly 20,000-year cycles. And then afterwards, you're pretty much only in the grassland and wooded grassland component. Even more interesting is that we can tell that we have cyclicity between moist tall grass and dry short grass, which in the modern ecology supports very different types of herbivores. So we have not only sort of transition from closed to open, but even variation within these open habitats. And so the sort of take-home message from this is that these orbital parameters and shifts in global climate patterns are definitely reflected in equatorial Africa, but that we also have this short-term variability that was much stronger than sort of long-term secular changes, right? So extreme environments and short-term oscillations are going to have important implications for changes we see in terrestrial resources that hominins relied upon. So jumping to the other end of the spectrum of our drill core still in Kenya, basically the last million years, we have the Koora Graben, which is part of the Olorgesailie site, and drilled by our sister project, the Olorgesailie drilling project, and Lake Magadi, which is only about 10, 15 kilometers away. And the reason we did these two sites is they're in the same climatic conditions, but different tectonic conditions. So we can try to tease out maybe some of the tectonic versus climatic influences. So the outcrop record at Olorgesailie has a great paleontological and archaeological record about the last 1.2 million years. And what we see there is the replacement of the Acheulean stone tools, the sort of hand axes, with the Middle Stone Age, and also changes in the fauna where you go from having large water-independent grazers, mega grazers, if you will, and then after this transition to an increase in smaller water-independent mixed grazing or browsing herbivores. The problem with the outcrops at Olorgesailie is we're missing actually the sediment and that important gap between 300 and 500,000 years ago. But it is captured in the core. And then again, you can see Lake Magadi here, just 10 or 15 kilometers to the west. So I'm not going to put up all the wiggles for this one, sort of a summary slide from one of the drilling project papers. But this summarizes about 10 or so different analytical techniques and proxies. And you can see that prior to about 400, 500,000, conditions were pretty stable in terms of the environments at Olorgesailie. And then afterwards, it becomes significantly more variable and arid than the older part. So going from top to bottom, you can see changes recorded in lake depth and water quality. Dry episodes is represented by periods of dry land exposure and soil formation, vegetation changes such as the decrease in woody cover, changes in C4 grasses again, and an overall change in resource availability, moisture, fresh water supply, things that are going to have real impacts on the fauna of which hominids relied upon and were part of. Excuse me. The record from Magadi is actually very similar to see what we see at Olorgesailie. The timing in the shifts are about the same. They have pronounced wet-dry cycles and increased variability over the last 500,000 years. But Magadi also shows sort of a little bit of a directional trend towards more arid climates, which you don't see at Olorgesailie. And long story short, this is probably due to some tectonic reorganization in the Olorgesailie Basin, which is, again, sort of a tectonic overprint over a more purely climatic signal in Lake Magadi. And so both cores indicate that sort of these middle to late Pleistocene environmental variability may have been drivers in the physical and cultural evolution of Homo sapiens and other sort of critters on the landscape at the time. So to sum some of these things up, we seem to observe what appear to be responses to both large-scale global and regional events, but not always, right? So we see sort of this picture at Baringo of this warm Pliocene to this cooler Pleistocene. Lake Magadi and at Lake Magadi, but not necessarily Olorgesailie, we see sort of this progressional shift in the last million years. What's interesting is at Turkana, where I didn't talk about, but we targeted that 1.8 million year interval, where we expect things to become, based off other records, a bit more arid, and we don't see that in the core, actually. And so there's sort of variability in what are the large-scale shifts being preserved at these different spots in Africa. It's not a, one site is the same as all the others, right? It's not a, I'm sort of looking for one size fits all, thank you. The orbital scale variability is observed in these drill cores, right? Especially this 20,000 year cycle that we see. We see other cycles as well, but it seems like that backdrop of that 20,000 year cycles is always recorded in addition to some of these other cycles. Some of the higher resolution analyses I didn't have a chance to talk about, you can see on the left these very finely laminated sediments. They've actually been cut out with razor blades to look at least centennial, if not annual resolution. Some of this work has been done at Turkana as well, that we see proxy records that are responding on the order of at least centuries, right? So things that you're not going to respond to anatomically, but you may respond to behaviorally in terms of your behavioral adaptations and stone toolkits and things of that nature. At present, we haven't gone through all the cores the same way. The core records tend to support or lend to support to the hypotheses related to environmental variability a bit more than progressive change, right? We still see some of that progressive change, but we see a lot of the variability being reflected in these cores and having impacts on the landscapes. And now our challenge is to integrate these high-resolution core records with the lower-resolution fossil records. We don't get century scale resolution, or even sometimes 20,000 year resolution at the fossil sites, at least not of fossil sites of this age. Now we have a challenge where we have the environmental records that are great, but they're at such a high resolution that now we're still trying to figure out how we integrate the paleoanthropological records. Lots of these are still being analyzed. There's still other drilling projects going on, which we're really excited about, and we'll see what's more to come. And this is just some of the HSP, DP, locality leads, and people that I've grabbed contributions to for this talk. So thank you, guys.